Welcome to this explainer. Today we're unpacking a genuinely revolutionary paper, one that completely rethinks what we mean when we talk about intelligence in artificial systems. It challenges decades, literally decades, of assumptions about how we train machines to explore, learn, and understand their environments. And honestly, it proposes this incredibly elegant, unified mathematical solution to some of the biggest roadblocks in modern computing. Let's dive right in.
So we got to start with a massive, mind-bending paradox in machine learning. Imagine you build an algorithm, right? And it's perfectly designed to seek out new information, which makes total sense if you want to drive exploration. But when you actually deploy it, this system just sits there and stares at random static on a noisy TV screen forever. Like, why on earth would it do that? It sounds crazy, but it's a very real problem researchers have been banging their heads against.
Section 1. The AI Learning Paradox. To understand this bizarre behavior, we need to look at the two main drives we historically program into AI. On one hand, you have novelty search, where the AI is told to maximize surprise. But this is exactly where the AI gets absolutely mesmerized by a noisy TV screen. Because the static is completely random, every single frame is 100% surprising. The AI thinks, wow, I'm doing a great job, but it's learning absolutely nothing. Then, on the flip side, you have the free energy principle. Here, the AI is programmed to minimize surprise. What happens? It just goes and hides in a dark room where literally nothing happens. Why? Because nothing is easier to predict than total, unchanging darkness.
The crucial takeaway here is that both of these approaches completely fail for the exact same reason. They conflate the total amount of surprise in a data stream with the actual, useful structure a bounded observer can absorb. And by bounded observer, I just mean a system with a finite compute budget, which is pretty much every real-world system. They treat all surprises equal, whether it's a brilliant new insight or just total useless noise.
Section 2. Unlocking Learnable Novelty. Well, the breakthrough concept that solves this paradox relies on a really cool metric the authors call epiplexicity. You can basically think of this as learnable novelty. Epiplexicity is the exact measure of what a learner can actually digest and turn into real knowledge. It totally ignores the useless noise of the TV screen, and it ignores the boring predictability of the dark room. It focuses strictly on the structure that a bounded mind can actually carry away from the data. This beautifully illustrates the solution. Think about the total surprise in any stream of data. It can be split into two parts: the learnable structure, that's our epiplexity, and the unlearnable residual noise. So by optimizing an AI to seek only the learnable structure, it naturally avoids both extremes. No more noisy TV because there's zero structure to learn there. No more dark room because there's zero novelty. It hits that perfect Goldilocks zone of rich, structured exploration.
Section 3. The Reservoir Computer Shortcut.
Okay, but there is a bit of a catch. Evaluating what a finite computer can actually learn usually requires running this massive, incredibly expensive search for every single data point. Finding the absolute best bounded model takes way too much time and computing power. It's just prohibitive. So to get around this, the researchers came up with a brilliant reservoir computer shortcut. Instead of training a massive neural network just to score the novelty, they pass the data through a fixed, random mathematical filter, they call this the reservoir, and then apply a super simple linear readout layer. It's genius because it turns a huge computational headache into a cheap, elegant estimator using a closed-form ridge regression. Now, what's a real game changer about this shortcut is that because it's a simple linear regression, epiplexity becomes fully differentiable. If you know machine learning, you know that means we can use it as a direct, real-time training objective. We aren't just measuring an AI after the fact, we can actively use its gradient to drive the system's evolution, step by step.
Section 4. Creating complex dynamics.
So how does this actually play out in practice? The authors started by testing their math on basic cellular automata. Those are simple grids of pixels that evolve based on really basic rules. When used purely as a measurement tool, this equation perfectly ranked the systems. It put the highly complex Rule 110, which is proven to be capable of Turing-complete computation, by the way, at the absolute top of the scale. On the flip side, simple, trivial, repeating behaviors like Rule 2 scored incredibly low. This mathematical objective essentially proved that it naturally favors systems right at the edge of chaos, which is exactly where complex computation thrives.
But wow, it gets even more astonishing. When they actually use this objective to train a neural network from scratch, meaning no human supervision, no predetermined rules, the AI spontaneously evolved what physicists call solitons. These are complex, traveling structures that literally collide, interact, and transfer information across the grid. The AI essentially generated its own complex physical laws just by trying to maximize its learnable novelty. How cool is that? Section 5. Unsupervised learning and exploration.
Now, this theory isn't just for abstract cellular grids. It flawlessly extends into some highly practical domains: representation and behavior. The researchers fed the AI a massive dataset of handwritten digits, the famous MNIST dataset. But here's the kicker. It was told absolutely nothing about what the images were. No labels at all. It was just told to maximize learnable novelty. To do that, the algorithm had to shed all the redundant information, like the black backgrounds, and focus purely on what made each image structurally unique. The result? The AI perfectly and spontaneously separated the 10 distinct numbers into beautiful, distinct clusters, completely on its own.
Finally, they put it to the ultimate test: reinforcement learning. This is training agents to navigate physics environments, like making a simulated robot walk or landing a lunar module. Often, robots just get stuck in these tasks, endlessly repeating bad behaviors. But when the researchers added learnable novelty as an intrinsic reward, the agent stopped stagnating entirely. Just by adding apoplexity, it improved the agent's performance over the baseline task reward in 9 out of 10 incredibly complex physics environments.
Because the AI is inherently motivated to find structure it can actually learn from, the bounded learner successfully pushed the agent to explore rich, new behaviors all on its own. It figured out how to pump a swing to gain momentum, or found totally new ways to balance. And the best part? It remained completely immune to the old noisy TV trap that used to completely derail AI exploration.
Section 6. Redefining Artificial Intelligence.
This paper really introduces a profound philosophical shift. We aren't just looking at a better piece of code here. We're looking at a new definition of intelligence itself. The authors wrote, "The intrinsic complexity of an automaton, the quality of a code, and the adaptivity of a policy thereby cease to be absolute properties of a system and become properties of a relationship." This shifts everything to an observer-centric view. Intelligence isn't just this absolute property baked into a machine's hardware anymore. Instead, it's a dynamic relationship between the environment's data and what a specifically bounded learner is mathematically capable of extracting.
And that leaves us with a truly staggering thought to take away. If artificial minds thrive in this exact mathematically definable zone of learnable novelty, if they avoid pure chaos and pure boredom just to find rich, structured learning, could this elegant math be the very engine of human curiosity? Are we, as biological learners, simply maximizing our own apoplexity as we explore the world? It's a fascinating lens to view not just the future of AI, but ourselves. Thanks for joining me on this deep dive, and keep seeking out that learnable novelty.